Okay, so in the second question, we're going to solve this problem in a geometric way. To do that, first of all, we need to draw the regions in the Descartes coordinates where both fx, the density function of x and the density function of y are non-zero. So it's just like this. It's actually a square, and the third one we need, and also we need to draw the curve that could explain that x plus y equals z, where z is kind of constant. Well, first we need to know that how such curves looks like. Well, it's just like, well, as we know, this is a linear function, so the graph is just like a straight line. It goes like this. When x minus y, x plus y equals z, with a slope of -1, and the intercept. Well, it's very important of this one. The intercept of the straight line on both x-axis and y-axis are all z. They're both positive. So as we know that OA and OB are both equal to z. Of course, we chose during our last speech, I chose A and B randomly. But we should know that OA is equal to OB. Okay. So having discussed the properties and characteristics of the curve of x plus y equals z, we're gonna first find out how z is valid. That means only as the straight line could pass the dotted area will z is a valid random variable. By saying valid, I mean that the density function of z is not zero. Well, if the straight line falls out of the area, and the density function of z will absolutely become zero. If we don't know the conclusions we have already drawn in the first question, we could do this. We could do this too. It's called a linear optimization. We have already learned in our high school, and we could get the minimum of x plus y. It's 1. Given the certain range of x and y like this, we could just draw this like this, and we're gonna consider the edging situations. Well, when z is the lowest, we could see that when z is larger, and the straight line just move like that in the direction of northeast. So a minimum z that could cause the straight line could have a common area of the square is that when z equals 1. In that case, the straight line will pass P, and the maximum z that could have a common area of the square is when z equals 3. Which means that the straight line will go past P, and the other they have a common area of only 1 point. Okay, so anyway, we get the valid area of z. That means between 1 and 3. Now we need to we need to calculate the density function. By saying a density function may be very hard to get, but the probability is not hard. We know that the density function, the probability function where z, capital Z, when the variable z is smaller than a certain z, equals to the probability that x plus y minus z. Well, we could write that, but we should, next step, we need to depict that equality in the Descartes coordinates. So let's illustrate how. As I've already said that as the straight line moved it moved northeast, the z is becoming larger. So otherwise, so vice versa. When we want to know that x plus y is smaller than something, what we need to do is to move it this way. It's like southwest, which means that the southwest part of the straight line, it's the area we're caring about. However, in order to make z a valid a valid random variable, the area should also falls into the valid area of x and y. So in summary, the area should fall into it should be circled by the straight line and also the side line of the square. So we're gonna try this. The area start from this, and we're gonna move. Okay, so we know as long as we know there's an area that circled out, we could just deduct the probability should be the area over the area of the square. We just simply write S P Q R. Well, the denominator, we could easily calculate that. It's just 1 multiplied by 1. So this is actually, the area of the square is actually 1. What about the area of the probability we're caring about? Okay, so that's needs some the little trick. When we move the line, and when z, it seems that when z is smaller than this, the area we're talking about, the black shaded area, it's a triangle. But if we move z to larger than this, and we continue moving the straight line, we're gonna see like this one. Then the area we care about, it's actually a square plus except the triangle. It's actually okay. Let me see. 1, 2, 3, 4, 5. It's actually a pentagon. Sorry, we're caring about. It's actually a pentagon. So we have to discuss this problem into 2 different situations. First, we need to know what does z reach when the area we're regard to it's still a triangle. It's that's very easy to find out, because the diagonal of the square it could fall on a straight line, which is x plus y equals 2, which means when z, so we get when z it's between 1 to 2, the area we're referring to, the shaded area, it's a triangle. So we just calculate this area, and we know that the intercept it's z of both axes, but this is not the area we care about. The area we care about is the shaded area. So it's like this, and we're gonna write it's 1. So the one that is in the square should be z minus 1. And the other side is also z minus 1, so we have z minus 1 squared. And also we need to multiply by 1 over 2 because we're talking about triangles. So this is the area. Well, the probability should be the area divided by the area of the square. That is 1. So finally we get the area of that. Okay. this is just a probability function. So actually, this is the probability we're talking about. Now we need to know the density function of it. So we're just gonna derivative. So just gonna derivative our probability function, which is z minus 1. This is exactly what we got. What we already part of the answer we got in our previous question. So we could verify that this is correct. Well, so we get it. So we get when z is between 1 and 2, the probability density function is z minus 1. We're gonna do okay. We conclude our first situation. In the second situation, when z is between 1 and let's look at that. It should be 3. We've already discussed that. It should z between 2 and 3. Sorry, 2 and 3, and we need to calculate the shaded area becomes the pentagon. And we just, in order to calculate the area of the pentagon, we only need to subtract the triangle on the right side. This is actually a right triangle. We can subtract the area of the triangle from the area of the square. So the area of the triangle, it may be so easy to see. The area of, in order to know the area of the triangle, we only need to know the length of one side. That is the length of AR. In order to know that, we need to do some auxiliary lines. Well, because all those points are 45 degrees. So without doing some rigorous mathematics, well, we can. We just don't. We could ignore it. We could conclude that this four-sided thing is actually a parallel, which means that the length of AR equals to, well, this is 3 and per limit, and the right side is z. So we actually are talking about, so the area of the triangle, this triangle, is 3. So the length of the triangle, so the length of one side of the triangle is 3 minus z, and we get this area like that. So the whole, area of the pentagon is 1 minus that. So when z is between 2 and 3, we get the probability equals to 1 minus 1 over 2, 3 minus z squared. And we're going to deduct this. We're going to take the derivative, and that equals to z minus, 3 minus z. You can do it yourself. Well, that actually matches the solution we concluded in our first question. So we can verify it is correct. So having reached all that, now that we have concluded that we have solved this question in a geometrical method, even though this is not the easiest way as for this very problem.